Hello everyone and welcome to video number 6 in FEMM 4.2 course. As you know, in video number 3, we looked for how to start FEMM step by step. In videos 3 and 4, we looked for electrostatic application. So now it's about time to look for electromagnetic application. Let's start. For the magnetic circuit or electromagnetic system shown in the figure below, we need to model this system using FEMM 4.2 as electromagnetic planar problem. We're going to choose the depth 16 mm. The coil has 25 ampere and 100 turns, and all dimensions are given in millimeter. So what we need to determine the normal tangential flux density components. We need to plot the flux density for the specified contour. Where is the contour? So the contour is here. And we need to show the tensor or the vector plot in our model. Also how to calculate the inductance using the FEMM 4.2, and we need to solve the problem for the iron with permeability 2000 and the M50 type. So this is a problem data. We have a coil of 100 turns, 25 ampere copper, 16 millimeter depth, planar solution. We are going to solve the problem for iron with relative permeability 2000 and for M50 type. So we are going to choose a base point or the origin point. So we are going to select that one. For example, that one will be the 0, 0, and all the other points are related to this one. So for example, this one is 64 and 0. That one will be 16 and 24 and so on. So here in the problem, it's given the current 25 ampere, but sometimes we can give you current density, ampere per millimeter square. So how to calculate the current from current density? So I equals kJAW over N. So K is called the filling factor. So we are going to fill this area by the conductors or the copper. So definitely we have insulation, we have bobine and some stuff. So K varies between 0.2 to 0.5 or 0.6. It depends on the application. For a magnetic circuit like this one, K could be something like 0.2 or 0.3. For a transformer, could be something like 0.5, 0.6 or 0.7. J is current density in ampere per meter square or ampere per millimeter square, and AW is the window area, and N is the number of turns. As we can see here, this is a structure after we draw it using FEMM software and added all the materials, but I like to focus on the materials. So properties, materials, we have air, iron, M50 and copper. So I'm going to leave M50 now, so we are going to focus on iron. Let's click on iron, modify property. So we are going to add the relative permeability 2000 X and Y directions. So that one is okay. So that one is iron and this blunger is iron as well. So this area is air and that one, if we click on this one, so this one and this one are the boundaries. So back to this one, what about this block? That one is a copper. So going to properties, materials, I'm going to choose copper. So for coppers, I'm going to click modify properties. So the mu R for the copper is 1, but electrical conductivity is 58 megasiemens per meter. So if we put that one, so now that one is copper. So how to adjust the circuit? So let's click OK. So going here, right click, space bar. So that one is copper block. And we are going to choose that one in circuit number 1. So how do you adjust the circuit? Let's go back. Cancel that one. Going to properties, circuits. So I'm going to have circuit number 1, modify property. I choose a circuit number 1, 25 ampere. So show us how to add a circuit. So add property. So we are going to choose a new circuit. Let's call it circuit 2. We can choose that one, for example, 100 ampere. Okay. So now we have circuit 1, circuit 2, whatever you like. So we are going to choose circuit number 1 and then click OK. Let's go back again here. Right click, space bar. So we are going to say this block within circuit number 1, and we are going to choose a number of turns minus 100. Why is minus? Because I'm assuming that minus 100 means the current is in. That's OK. And for that one, right click, space bar. So that one is the same circuit, so the current is out now from the other side, but number of turns is positive 100. This means that the current is going out of the page. So I assume now that if the current is in and the current out, so the flux is going in this direction. So we are going to solve the problem and see the results. I added some points here just in case if I like to check the flux at any point, and I added these 2 points to plot the contour. So before solving the problem, let me remind you about the problem adjustment. So choose planar, millimeter, 16 millimeter in depth. Okay. So if you click here, you can snap to grid, enable or disable. About the grid size, we choose 10 millimeter for the grid size. Okay. So it's time now to create our mesh. Let's click on that one. We have here 40,929 nodes. Okay, so we notice that compared to the previous videos, we have a huge number of nodes. So why in this video we have this high number? So assume that we are going to enable this one, click on the iron, right click, space bar. Look here, we have mesh size. I adjusted that one to 0.5. But if we click here, let triangle choose mesh size. So click OK, and we are going to remesh again. So let's try it. Now the number of nodes is dropped to almost 30,000. And you can see here white spaces as well. So it's up to you for the mesh size. So I'm going to return that one back to 0.5. I'll disable that one. I'm going to make the mesh size 0.5. Okay. And I'm going to create the mesh again. Okay. So it's time now to solve the problem. So now we are ready to see the results. Firstly, we are going to check the flux density at different points. So we are going to click here, show density plot. Okay. As we can see here, the color is almost green. So we are in this region, something between 0.5 to 1.4 Tesla. There are some points are in the yellow part. So we are going to check the flux density now at different points. For a point like this one, we have the flux is 1.275 Tesla. At a point like this one, we have 1.1 Tesla. In the air gap, in the top side, we have 0.75. In the lower one, we have something like 0.75. This is the magnitude of the flux. But for a point like this one, let's check here. So we have something like 2.45 Tesla. So that one is a sharp corner. So your task is going to repeat the problem. And rather than to make that one as a sharp corner, make it like an arc with 45 degrees and check what is the flux here. We need to look for the flux now as a pattern. So we are going to select this line. I'm going to enlarge this one. Going up, choose this point. Going down, choose this point. So that one is a contour. Going to the graph, plot the magnitude of flux density. So as we can see here, we have in the top and bottom, we have 0.75. And in the middle, we have a flux almost zero. What about the normal component? So let's go for the normal component. So the normal flux density, okay. So we have in the top part, we have positive 0.75. This means the flux is going out. But in the bottom one, we have negative 0.7 or 0.75. It's close to that one. So this means the flux is in. But we need to confirm that one by another way that the flux is going out and in. So let's check for the tangential component first, which my anticipation should be close to zero. Okay. So we have a spike here, but in the middle of the magnetic circuit, we have zero flux density. So we know that the magnitude of the flux is root P normal squared plus P tangential squared. So I'm going to return the problem again. Let's choose another contour. Choose this one. Plot the flux density again. And if we look here, we are going to find that the flux is constant, something like 1.3 or 1.27. So why is constant? Because that one is a coil here and that one is a source of the flux around this limb. So that one is constant flux. So the flux is concentrated here. How do we know the direction of the flux? So if we're going here, we are going to disable the flux lines. Okay. And choose this one. I'm going to select the flux density B. Let me make the scaling factor 2. Okay. What we can see here, this is the direction of the flux. It's going up, out from here and into this part. So out, in, out, in. So that one is called the tensor or the vector plot. Show me the direction of the flux. You can control the size of this arrow. So if you make it 4, for example, I'm going to see it bigger. So let us disable this one now. So I'm going to select for that one, none. Okay. And then I'm going to return back to the flux lines. Show flux lines. So if we click on this one, we are going to find the inductance. So the total current is 25 ampere, the voltage drop is something like 0.27 volt, and the flux linkage is 0.032 Weber, and the flux per current is 0.00127 henries. So that one's something like 1.27 millihenry. Can we calculate the inductance by another way? Yes. So if we click on this one, choose this area, and then we are going for the integration part. So that one is going to give you different values. Here we have A dot J, we have A, magnetic field energy. Let's click A dot J, for example, what that one? So that one is Henry ampere square. So if you have this value 0.797387 and you divide that one by 25 square, is going to give you the same value for the inductance, because that one is Henry ampere square. So divide this value by the current square, give you the inductance. If you solve that one, you are going to find the same value is calculated from here. So that one is something like 1.27 millihenry. What about the force for this blanket? I'm going to disconnect this one or disable this one, select this blanket. So now we are going to check for the force. Force via weighted stress tensor. Okay, so what we are going to find here, that the force in the x component, so this means that the force is going in this direction, is going to pull that one in this direction, and this is why we see the negative sign, because we are against the air gap. So that one something like minus 127.985 Newton. Let us return back to our problem, and I'm going to purge the mesh. I'm going to change the iron to M50, so right click, space bar, I'm going to choose that one, M50. Okay, this one as well, M50. So how do you know the pH curve for that one? So let's go for properties, materials, and we're going to choose M50 modify property. When we look here, that one is nonlinear pH curve. So we're going to edit the pH curve, so give you the numbers for B and H. But if you like to plot pH curve, click here. So that one is going to give you pH curve, but that one is not clear. So we can look here for a log plot for pH curve. If you like to have the linear relation between B and H for this M50 iron, so you can find the value here, something around 1250. So that one is mu R, the relative permeability. So assume for the iron, I'm going to click for the iron now, cancel that one. I'm going for the iron. Modify property. So we choose linear, but if we choose non-linear, we can edit the pH curve by ourselves and we plot it. But I'm going to return back to this one now. Okay, so that one is M50 and that one is M50. We have the copper. So now we are going to create the mesh, run. Now we can see the results if we click on this Google. Let us show the density plot. So compared to the normal iron, the color is different, but the range is up to 1.472 Tesla. So we have a flux density something like 1.5. Compared to the normal iron, we reach something like 2.7. But in the air gap, what is the flux density? The flux density is the same, almost 0.75. But in a point like this one, something like 1.1, and in a point like this one will be 1.27. Almost the same, except that the saturation parts is lower using this type of iron. So what about the inductance? So the inductance for this one, flux per current, will be almost the same value, 1.27 millihenry. Okay, we can calculate it using another way. That's check for this one. So we are going to select these two areas and then we are going to integrate the first one. So that one is almost 0.797 Henry ampere square, which gives you the same inductance almost for this magnetic circuit. What about the force? I'm going to disconnect this one here or disable this one. I'm going to choose this one and then integrate here, going to the force. Okay, we're going to find that the value is almost the same, minus 128.14 Newton. Negative because that one is going to be opposite to the direction of the air gap. So I'm going to choose finally, I'll show you finally here about the contour. So if we choose a contour here in the air gap, choose this point and this point, graph. What is the magnitude of the flux density? So we have here something like 0.75 and 0.75 for the top limb or the bottom limb as well. So M50 is close to the normal iron. The answers could be different. You can try it with yourself, that if you change the relative permeability, rather than to be 2000, something like 200 and something like 100,000. So let's return back to our slides now. As a summary for this video, we built a simple electromagnetic model based on a magnetic circuit similar to those used in relays or transformers. We assigned the magnetic properties of iron by defining its permeability or implementing a pH curve for a specific material, something like M50. We refined and adjusted the mesh to study its effect on accuracy, and we analyzed the results by plotting the magnetic flux density along a selected contour line and visualizing the magnetic field using vector plots. Finally, we calculated key electromagnetic quantities, something like inductance and force. I hope you enjoyed this course and thank you for watching.